For our last section on forces, we're going to talk about two particular forces that play an important role in our environment here on Earth, which is gravity and friction. So first we're going to talk about gravity. So whenever we have an object that's falling through the air under no other force but gravity, we call that free falling. So the motion of a body when only the force due to gravity is acting on that. And Earth always accelerates these objects at the same acceleration. So 9.8 meters per second squared. So no matter what object is falling, where it's falling on Earth, Earth always pulls downwards or accelerates it at a rate of 1.9 meters per second squared. And so acceleration due to gravity, that number 1.8, does not depend on the mass of the object. So whether that object is a hammer or a feather, they should fall at the same rate if we ignore air resistance, okay, which creates friction resistance motion. So if we were to get rid of air resistance, drop a hammer and a feather, they should hit the ground at the same time. Now on Earth it's hard to do that because we have air, but they did do this on the moon. So on Apollo 13 mission, they did drop a hammer and a feather, and we'll see if they hit the ground at the same time. Now Earth's or Moon's gravity is a little bit different, but it would work the same way as on Earth.
Tim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Okay. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his.
Okay, so no matter on Earth, no matter the weight or the mass of our object, if we ignore air resistance, they should hit the ground at the same time. So Galileo Galilei was the first one to do this experiment. Remember, off the Leaning Tower of Pisa, he dropped two balls with different masses, and they hit the ground at the same time. That's because Earth is accelerating them downwards at the same rate, 9.8 meters per second squared. Now, they repeated this experiment on Earth in this next video, and it's a little bit long, so if you want to go back and watch it, you can. But they take a feather and a bowling ball, and they do it in a vacuum chamber. So a vacuum chamber is a chamber that they remove all the air from. So there's no air resistance then. And they drop them at the same time, and you can visually see them hit the ground at the same time. So if you're interested, go back and watch this video. So when we talk about gravity, a lot of times we talk about the term weight. So let's define the difference between mass and weight. So mass is the amount of matter an object has. So as long as you have the same amount of matter on your body, your mass will stay the same. So no matter where you are, on Earth, on the moon, on Jupiter, your mass is the same. And so we measure mass in the unit called the kilogram. Weight, however, is a little bit different. So weight is the force of gravity pushing down on that matter. So weight is a force. So it's measured in newtons. And depending on where you are, your weight will change. So on Earth, your weight is whatever your normal weight is. But on the moon, your weight would be different because the gravity is different on the moon. So you'd actually weigh less. On a planet like Jupiter, where gravity is more than Earth's value, you would weigh more. And so weight is a force. So how much gravity is pushing down on your matter? So we calculate weight by using an equation here. And remember, weight is a force. So it looks very similar to our equation we've talked about before. F equals ma. Okay, except this time, instead of force, we have a specific force, which is weight, with W. M still means mass. And G, we have a specific gravity or acceleration. So that would be 9.8 meters per second squared. So gravity G on Earth is 9.8 meters per second squared. So you can see here how your weight would differ on different planets and bodies in our solar system. So to calculate your weight, you take the mass of your object in kilograms times the gravity. Most of the time it's going to be on Earth, so most of the time it will be 9.8. Let's try an example. So what is the weight of an object that has a mass of 56.3 kilograms? So we're going to use our equation. Weight equals our mass, which is 56.3, timesing it by our acceleration. So it doesn't say we're on a different planet, so 9.8 is the acceleration on Earth. So if we calculate those two by multiplying them together, we get a weight of 551 newtons. So N, because it's a force. Okay, let's try another one. What is the acceleration? So we need to find our gravity. On Venus, if an object weighs 75 newtons, so our weight is 75, and has a mass of 25, so M is 25, and we need to solve for A. So to get A by itself, we're going to divide both sides by 25. So it cancels here. So we're going to take 75 divided by 25, and we get an acceleration of 3. And units are meters per second squared. The other kind of force we want to talk about is friction. So friction is the force that opposes the motion of two surfaces. So when we're sliding or moving across the surface, we experience a force in the opposite direction of our movement. So if we're moving to the left, friction works towards the right. So sliding a box across the floor, an object falling through air, rolling like a tire across the ground, all of those are going to experience some kind of friction. And if we were to look at the micro level, we would actually see these bumps. And that's what's happening at the surface. They're getting caught. And so we experience a backwards force that opposes our motion. And the more force we apply, the more friction we experience. So there are two types of friction. One is called static friction. So static means not moving. So this is the friction that opposes a surface from moving. So if you have a box on the floor and you're pushing with all your force to try to get it to move and it still doesn't move, that's because static friction is too large. So static friction keeps an object from moving. So if your car is parked on a hill, what keeps your car from rolling down that hill? That's static friction. So it's opposing what would be the normal motion. So in order to get an object to move, you have to overcome that static friction. So it keeps an object from moving or from sliding past one another. So once our object is in motion, though, we call that kinetic friction. So this is the friction that opposes the motion of two surfaces that are moving past one another. So when you're driving down the road, the tires on the road experience static friction. Or once you get that box sliding, you still experience some backward force. So that is called kinetic friction. So object not moving, that's static friction. Object moving is kinetic friction.